Welcome to the survey of the elementary principles in classical mechanics. In today's video, we are going to discuss the mechanics of a system of particles. When applying Newton's second law of motion for particle I within a system, we must distinguish between the external and internal forces acting upon it. So the total force acting on the particle has one component, the external force, which is acting from outside the system, and then there is a collection of forces which are generated by all the other particles that are acting on particle I. And these are summed over the index j, where j is different from I, which underlines the fact that particle I cannot interact with itself. We assume that both types of forces in the above expression must obey the weak law of action and reaction, which is the original formulation of Newton's third law. That is, the forces two particles exert on each other are equal and opposite. If we then sum over all the particles in the system, so if we take a sum over I in the formula here, then the right-hand side is simply the second-order time derivative over a sum over all the particles in the system, where each term of the sum is the radius vector of the corresponding particle weighted by the particle's mass, and this has to be equal on one hand with a sum over all of the external forces, and this amounts to the total external force being applied to the system, and a sum over internal forces added up for each particle. So it is essentially a double sum or a sum over pairs of forces, and this must be equal to zero by virtue of the fact that these forces are assumed to obey Newton's third law. In this case, we can define what is known as the center of mass, and which is denoted by capital R, and it is equal to the sum over all particle radii weighted by the corresponding particle masses and divided by the total mass of the system. With this definition, Newton's second law takes the simple form of the total mass of the system multiplying the acceleration of the center of mass being equal to the total external force that is being applied on the system. So the center of mass moves as if the total external force acted on the entire mass of the system concentrated at the center of mass. Internal forces obeying Newton's third law do not affect the motion of the center of mass. Examples of this idea are exploding shells under the assumption that we can neglect drag forces with the atmosphere, and this idea is also behind the principle that makes jet and rocket propulsion work, which is something that we will discuss in greater detail in the second part of this series. As an illustration, assuming that we have a system of coordinates with an origin O over here, and then the particles within our system are represented by the dark circles, we can highlight, for example, the particle of mass mi by the radius vector ri, or the particle of mass mj and radius vector rj, and in this particular case, the center of mass corresponds to the imaginary point here, denoted by an empty circle and having the radius vector capital R. So this is the point that is going to move as if the entire mass of the system were concentrated at it and the entire external force was being applied to it. The magnitude of R is given as follows. If we start from the definition and we square it, we obtain that total mass squared times capital R squared must be equal to a double sum over products of masses multiplying the corresponding dot product between particle radii. Now, the square distance between two particles follows very simply from the definition of their relative vector as the difference between their two radial vectors with respect to the origin of the coordinate system, we just take the square of this expression and we find that it is equal to a sum of squares for the corresponding radii minus 2 times the dot product of the two radius vectors. And if we then solve this equation for the dot product, we can express it as 1 over 2 multiplying the sum of squared radii minus the square of the relative distance between the particles. And then if we bring this back up into the sum here, it follows in a very straightforward manner that m squared times r squared is equal to the total mass multiplying a sum over all particles taken for the mass of each particle multiplying its squared radius vector minus 1 over 2 multiplying a double sum over the products of masses and the corresponding square of the relative distance. Assuming that equation 122 holds, so namely that the total mass times the acceleration of the center of mass is equal to the total external force, then if we once again write Newton's second law in its general form for a given particle and we sum over all the particles, we obtain the familiar result where the left hand side is just the total mass times the acceleration of the center of mass, and on the right hand side the first term is the total force acting on the system and the second term is a sum over all internal forces summed over all the particles within the system. But now by virtue of this assumption, which is taken from the very beginning, the immediate implication is that this sum must be equal to 0. Therefore, under the assumption that Newton's second law can be written in this form for a system of particles, it means that the internal forces obey Newton's third law. That is, they are equal in magnitude and opposite in direction for each pair of interacting particles. We can now discuss conservation theorems within the context of many particle systems. And the first such theorem regards the total linear momentum, which for a system of particles is defined as the total mass of the system times the velocity of the center of mass. So the expression here. And the conservation theorem is immediate, its statement being that if the total external force being applied to the system is 0, then the time derivative of the linear momentum is 0, and as such the total linear momentum is conserved. If we want to study the conservation theorem for angular momentum, first of all we must write Newton's second law for a given particle, let's say particle I within the system. We take its cross product with the radius vector of the particle and then we sum over all the particles. On the right hand side we will obtain a familiar result, namely this cross product is simply the time derivative of the angular momentum of particle I. And we already know this because, as we have seen previously, if we take the time derivative here, this becomes the velocity of particle I, and this vector will be parallel with the particle's linear momentum. And as such, this term of the cross product vanishes. When we sum over these time derivatives, the result is the total time derivative of the angular momentum of the system, and this has to be equal, first of all, with a sum over all external torques being applied to the system. So this is just the total torque that is being applied from outside, plus a sum over all of the internal torques that are due to the internal forces acting between pairs of particles. This term is made of a sum of pairs of the form written down here, and by virtue of the fact that these internal forces must obey Newton's third law in its weak form, it means that for the force here we can interchange the indices to j and I, and this will amount to a minus sign in front of the cross product. As such, each term of the sum is a cross product between the internal force acting on the two particles and uh, their relative radius vector. As an illustration, if we consider the same system of particles with respect to some origin O, if we have the radius vector Ri of particle I and the radius vector Rj of particle j, then their relative vector Rij lies along the line joining the two particles and is directed towards the particle I. If in addition to being equal and opposite, the internal forces acting on two particles are also along the line joining the particles, then we speak of the strong law of action and reaction. In this situation, all cross products vanish and the time derivative of the angular momentum is going to be equal to the total external torque being applied to the system. As such, the theorem for angular momentum conservation states that if the external applied torque is zero, then the time derivative of the orbital angular momentum is zero, and as such the angular momentum is conserved. It is important to stress that the above is a vector theorem. A component of the angular momentum can be conserved if the corresponding projection of the external torque vanishes, even if others do not. And this is a situation that is very common in many physical systems. It is also important to stress that the conservation theorems for the linear momentum and for the angular momentum rely on the weak and strong form of Newton's third law. However, this law is not valid for all kinds of systems, as is the case, for example, for a system of moving charges. And this is something that we are going to study towards the end of this video. Now, if we assume that equations 122 and 126 both hold, that is, if we are assuming that the total mass times the acceleration of the center of mass is equal to the total external force, and that the time derivative of the orbital angular momentum is equal to the external torque being applied to the system, then if we write Newton's second law for the angular momentum, we arrive at this expression, which is familiar, and we already know that in these conditions the second sum on the right hand side must vanish. And we can write this in two ways. This is the same expression as the one in Newton's second law, but we can write it equivalently by changing the I index to j and j to I. So this is simply a relabeling of the indices. And now, by virtue of this being valid, so by virtue of the fact that the internal forces must obey Newton's third law in its weak form, it means that we can interchange the indices j and I here, which amounts to getting a minus sign in front of the expression. And then if we add the two together, we obtain the result here. The sum that vanishes is a sum of cross products between the internal force acting between two particles and the relative vector joining the particles. So as such, these assumptions automatically imply that internal forces must obey Newton's third law in its strong form. They are equal in magnitude, they are opposite in direction, and they are also lying along the line joining the two particles, which is expressed here. We know that the linear momentum of a system of particles behaves as if all the mass were concentrated at the center of mass and moving along with it. However, this system may also possess an angular momentum, and we would like to see if we can describe the behavior of the angular momentum with reference to the center of mass of the system. To do this, we rewrite the radius vectors of all particles relative to the center of mass. So each radius vector is going to be equal to an r prime of index I plus the radius of the center of mass. And by taking the derivative with respect to time of this expression, we immediately obtain a very similar result for the velocities of the particles, written in terms of a velocity relative to the center of mass plus the velocity of the center of mass itself. With these expressions in the formula for the angular momentum, we obtain the cross product here, which has four terms. What the first term describes is the angular momentum of the center of mass itself as it moves about some external point of reference O. The second term of the sum is the angular momentum of motion about the center of mass. So this is the angular momentum of the particles that will be rotating around the center of mass. And the last two terms of the sum both vanish. The reason why they vanish is because they both contain the following sum over the radius vectors relative to the center of mass and weighted by the mass of the particles. So what these sums define is the radius of the center of mass in a reference frame where the center of mass is at the origin, and as such they add up to 0. As an illustration to make the point clearer, if we have a center of mass here at a radius capital R with respect to the origin O, and we have a particle I at radius Ri with respect to O, then R prime of index I is going to be the relative vector of particle I with respect to center of mass. So it is clear now that if we were to sum up the vectors of all particles with respect to this point, the total sum is going to be equal to the coordinates of this point at the origin of the system. So the net result is 0. If we want to study the conservation of energy, we must once again begin from the definition of the work done to the system by the total force being applied to it. And this is simply going to be a sum over line integrals for each particle in the system, where the integrand is going to be the total force applied to the particle. And this decomposes into an external force and a sum over the internal forces done by all the other particles in the system acting on our chosen particle. Written in the general form here on the left-hand side, the result is quite trivial. We already know how to do it for a single particle. So each such integral is equal to the difference in kinetic energy between the endpoints of the trajectory for that particular particle. So when summing everything up, the total work amounts to the difference between the total kinetic energy of the system in the initial and final state. And the total kinetic energy is at any point along the path defined as the sum of the individual kinetic energies of all particles. Now, we can write the kinetic energy in terms of velocities relative to the center of mass by using the expression in equation 127. And then if we work out the dot product, we obtain three terms. The first one is simply equal to the total kinetic energy of the center of mass. The second one is the kinetic energy of motion relative to the center of mass. So it's going to be the kinetic energy of the particles as they move around the center of mass. And the last term vanishes by virtue of the previous argument, namely because it contains this sum, which amounts to the coordinates of the center of mass in the reference frame where the center of mass is located at the origin, and as such the sum is 0. Now, for conservative external forces, we can write each integrand as the gradient of a scalar function, and we obtain the immediate result that the total work must be equal to the difference in potential energy between the endpoints of the path for each particle and summed over all the particles in the system. If the internal forces are also conservative, they follow from a two-particle potential. So they follow from a function that for each pair of particles depends only on the relative distance between the particles. And in this case, it's very easy to show that if you take the relative distance between particles I and j and you apply the gradient with respect to the coordinates of particle I, then the result is a unit vector pointing along the line joining the particles and directed towards particle I. While if you take the gradient of the same expression but with respect to the coordinates of particle j, this is a unit vector pointing in the opposite direction, so pointing towards particle j. In this case, the forces are equal, opposite, and along the line joining the particles by virtue of the definition here. But this would not be the case if variables like velocities or spins would be involved in the two-particle potential, which in this case has a gradient that is equal to some scalar function f, which depends on the nature of the potential, and this function multiplies the relative vector between the particles. The work done by internal conservative forces on a pair of particles I and j is a sum of two line integrals corresponding to each of the particles. And since these forces are conservative, we can write uh, them in terms of gradients of the two particle potential, but we know that these gradients are as well equal up to a sign, so they can be factored out of the expression, and the resulting difference between differential line elements is simply the differential of the relative vector of the two particles. As such, uh, the line integral has the expression here, and uh, the result of this individual integration would of course be the one here. So it is just the difference in the value of the two particle potential between the endpoints of the path. However, if we sum this expression over all the particles in the system and do the summation for each pair of particles, we will end up counting everything twice. Because if we run the sum in such a way, we would take the potential once for particle I and j, but as we keep counting at one point we would be taking it again for the pair j and I. And as such, when performing the sum, we need to add a factor of 1 over 2 in front, which is there in order to avoid the double counting of pairs. If both external and internal forces are conservative, then the total potential energy is the sum of two terms. One is a sum of single particle potentials that are due to external fields interacting with the system, and the second term is a sum of two particle potentials, which includes all of the internal interactions within the system. And this is a very general expression found throughout all of physics, whether we discuss, for example, about electrons in an atom, or electrons in a conductor, or nucleons and protons within an atomic nucleus. We very often need to discuss systems having energy terms of the structure, and it is also quite common to be in situations where the external one-particle potentials are quite different in nature from the internal interactions between the particles. And on one hand, this leads to very interesting phenomena, but it also leads to many difficulties that need to be overcome when we want to understand the behavior of these systems. Now, with these considerations in mind, the sum between the kinetic and potential energy is conserved, but the internal potential is constant only for rigid bodies. That is, for systems where the relative distances between particles are fixed. And therefore, in such a system, a differential change in the relative distance must be perpendicular to the line joining the particles, or equivalently, the mutual force acting between the particles needs to be perpendicular to this differential change. So, in other words, in rigid bodies, internal forces can change the orientation of the particles, but they cannot alter the distance between them. In a rigid body, internal forces do no work, so the internal potential can be disregarded when analyzing the system's motion. We are now going to discuss examples of physical systems where the law of action and reaction is violated, and these particular examples are taken from electrodynamics, and they involve systems of two moving charges. And the two examples we will discuss are labeled by A and B. In case A, we will have 2 point particles of identical charge Q separated by a line segment that is parallel to the x-axis. And these two charges will have equal velocities v that are parallel with each other, but they are directed along a line which is not parallel to the line joining them. In case B, the initial setup will be similar, but for this situation we will have charge 1 moving directly towards charge 2, while charge 2 will be moving at a right angle from it. Upon a charge q located at position r at a time t and moving with velocity v in an electromagnetic field given by the electrical field E and magnetic induction B, the force exerted locally by the field upon the charge is known as the Lorentz force, and it is equal to the charge multiplying the local electrical field plus the cross product between the charge's velocity and the local magnetic induction field. Now, in the situation where the magnetic induction is due to the presence of another charge being located somewhere in space, then from Maxwell's equations it can be shown that this magnetic induction vector is equal to 1 over c squared, where c is the speed of light in vacuum, multiplying the cross product between that second charge's velocity and electrical field. And as such, the Lorentz force has the expression here where we need to be mindful of which vectors belong to which charge. So if, for example, this is the force done by the second charge on the first one, then Q here is going to belong to the first charge, while the electrical field belongs to the second one, and this velocity as well belongs to the first charge, while this velocity and this electrical field both belong to the second charge. Now, in case A, the force acting on the first charge is given as follows. The electrical component is just the charge multiplying the electrical field of its partner, and since we're working in the convention where the electrical fields are pointing away from the charge, away from each charge, and as such the result is simply q times ex and directing in the negative direction of the x-axis. And as for the magnetic component, It's very easy to first work out the cross product of the second charge's velocity and electrical field. This ends up being the y component of the velocity times the x component of the field directed along the z-axis. And then we need to take the cross product of the velocity of charge 1 with the unit vector along the z-axis, and the result is the one here. So adding the two together, we obtain the total force which charge 2 exerts on charge 1. And the first thing that we observe is that this force is not directed along the line joining the two charges. It has a component along that line, so along the x-axis, but it also has a component along the y-axis. For the second charge, in an identical manner, we obtain an electrical component that is equal to the one calculated previously up to the sign, and the same for the magnetic component. It is the same result up to the sign in front. So the conclusion is that these two forces are equal in magnitude and they are opposite in direction, but they are not along the line joining the particles. The law of action and reaction holds only in the weak form for this system. And the major implication here is that apparently, even if we do not act with an external torque on the system, there is still an angular momentum that is present due to internal forces. In case B, the force acting on the first charge is going to be once again given by this simple expression is just minus q times Ex, and the magnetic component has a similar structure to what was previously calculated, but now the only difference is that the velocity of the second charge is perpendicular to the electrical field. So the total result is the one here. However, if we now do the calculation for the second charge, things turn out as expected. For the electrical component, it's equal to the one calculated here, but pointing in the other direction. However, when we want to calculate the magnetic component, in this case, the velocity of the first charge is parallel with its electrical vector at the point where the field would interact with the second charge, and as such the magnetic component vanishes and the force with which charge 1 acts on charge 2 is purely electrical in nature. So in this situation, the second charge exerts a magnetic force upon the first charge without a corresponding reaction. Newton's third law breaks down completely, which implies that neither angular momentum nor linear momentum are conserved for such a system. In the particular case of electrodynamics, the way in which we can solve this apparent violation is by realizing that the physical system being discussed here is not solely comprised of the 2-point charges, but also of the electromagnetic fields between them. And these fields can as well carry linear momentum, angular momentum, and energy. And if we were to extend the definitions of these quantities beyond the mechanical context in which we have worked so far, then these apparent paradoxes or violations of Newton's third law would be addressed. More generally, however, this is a good starting point for a critique of conservation laws and the true meaning behind them. And a very interesting discussion on this topic can be found in the treatise titled Mechanics by Keith Simon. And in the following, I will summarize what I believe to be the most interesting points of the discussion. The laws of mechanics apply to three major classes of phenomena. Firstly, celestial mechanics, where the dynamics of the solar system can be predicted with great accuracy for thousands of years. Deviations due to general relativity are only observable in the slow precession of Mercury's orbit around the Sun at an angular velocity of roughly 0.01 degrees per century. Secondly, terrestrial mechanics is the field where the motion of macroscopic and microscopic bodies is properly described by Newtonian mechanics without significant corrections, but the laws of force are usually very complicated and not known precisely. The beauty of celestial mechanics cannot be wholly replicated here. And thirdly, we have quantum mechanics and quantum field theories, which are completely beyond Newton's program. Linear momentum is conserved in celestial and terrestrial mechanics, and even in quantum mechanics up to when high velocities or rapid accelerations are concerned. Gravitation and mechanical forces obey the law of action and reaction up to a very high degree, as do electrostatic forces. However, this is no longer the case for moving charges, case in which the law of action and reaction breaks down and momentum is not conserved unless we take into account the momentum of the electromagnetic field itself. This redefinition of linear momentum goes beyond the limits of Newtonian mechanics. Newton's second law holds for macroscopic bodies only because the internal forces between the particles found in their structure obey the law of action and reaction. Newton's second law is a fundamental postulate grounded in experimental observation and deeper physical theories. It gives a consistent theory of mechanics in the sense that, if we construct a composite body from smaller bodies obeying Newtonian dynamics, so will the composite body. Angular momentum as defined for a system of particles and its conservation law apply to terrestrial and celestial bodies that can be regarded as particles. That is, they do not exhibit internal rotation. In that case, the conservation theorem still holds provided that the additional angular momentum is included within the definition. The angular momentum of the solar system is very nearly constant. Tidal forces, however, convert some of the orbital angular momentum into rotational angular momentum, so that must be accounted for in regard to precise conservation. Friction with dust and rocks further changes the angular momentum, but this change can be accounted for by including the angular momentum of the debris itself. Total angular momentum is conserved due to the law of action and reaction, but this is no longer the case when we consider quantum systems. As quantum objects possess spin, the idealized point particles of Newtonian mechanics completely characterized by their radius vector are no longer a proper description. The conservation of angular momentum must either be accepted as a basic postulate, or we must appeal for its justification within theories that go beyond classical mechanics. The conservation of mechanical energy holds accurately in celestial mechanics, but even there exists a loss of energy due to friction and tidal forces within the solar system. Friction is even more important for terrestrial mechanics, where usual energy conservation theorems do not hold exactly in the mechanical sense. However, as was discovered by Joule, energy can be associated with heat, and therefore we can satisfy the theorem by extending the definition of energy to include heat. If bodies are made out of quantum constituents, heat is simply the energy of their random motion. Similarly, while electromagnetic forces are not typically conservative, energy is conserved when we extend its definition beyond the mechanical sense to include the energy of the electromagnetic field itself. Conservation laws are the cornerstones of modern physics. They are valid for material bodies not because of their simple structure of Newtonian particles interacting for central forces. They are not true laws, but rather postulates which must hold in any physical theory by redefining the meaning of the respective quantities. A conservation theorem is not a physical fact, but rather a consequence of our determination to make it so. The statement of a physical fact, which may or may not be true, is that such definitions can always be found. In summary, in this video we have extended the framework of classical mechanics to many particle systems by generalizing Newton's second law of motion. The center of mass has been defined along with an extension of the corresponding conservation theorems for linear momentum, angular momentum, and total energy. The breakdown of the law of action and reaction in electromagnetism has been discussed along with a general critique of conservation laws. In the following, we will discuss constraints placed upon mechanical systems. I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.